We are going to learn about how you can design a control logic using the microprogram control organization mechanism. Okay, so in the previous video we studied how you can design a control logic using hardwired method or one flip-flopper state method. Now this is the second method through which you can design a control logic. So all those who haven't seen those videos based on that one flip-flopper state method, please do watch that and come back and learn this video, because most of the things are repetition of those what we have studied in the previous video. So basically you won't get a flow if you start off initially studying with this mechanism. Okay, so coming to the microprogram control organization, so basically what is the difference between a hardwired and a microprogram control organization? In a hardwired organization, definitely there will be a lot of hardwired components and all those wires need to be rearranged every time a modification is being done. In microprogram control organization, obviously it will be a set of micro programs, or it will be certain control words that are used to design our control logic. So let's see what all are that. In a microprogram control, the control variables that initiate the micro operations are stored in memory called control memory. So there are basically certain control variables. These control variables will initiate a micro operation. This micro operation is nothing but our addition, subtraction, complement, transfer, etc. So all these micro operations are initiated by control variables and they are stored in memory called control memory. The control memory which we use here is ROM, because whatever that is being stored, that is the control, whatever stored in those control memory are made permanent. So that is the reason why we are using a ROM. Then the control variables that are stored in the memory are read one at a time to initiate the sequence of micro operations. So first control variable will be to perform an addition. The second control variable will be to perform a transfer or to perform a comparison. So each control variable is being read one at a time. Okay, and the word stored in control memory are called as micro instructions. So this word is called as a micro instruction, and each micro instruction will specify one or more micro operations. So basically these control words are micro instructions, and these instructions can be one or more micro operations. Okay, now once the micro operations are executed, the next thing is to specify the address of the next micro instruction. So suppose first an addition is being performed, so after that addition, which is the next operation that need to be performed, or what is the address of the location where that particular micro instruction is being stored, that should be given. So the micro instruction contains basically two things. It should initiate a micro operation and also it should generate a next address. So every micro instruction will have a micro operation, or it will have something to initiate a micro operation, and also it will have something to generate the next address. Okay, so a microprogram control unit must include special circuit for selecting the next address as specified by the micro instruction. So when you are going to design a microprogram control unit, the things that need to be kept in mind is that apart from reading a micro operation and performing that micro instruction, it should also have components to get the next address also. Okay, so basically all these control words that are stored in the memory are basically a certain set of bits. So it is said that each control word is said to have 14 bits. Okay, so like that maybe 8 or 9 or 10 control words will be stored in a memory in the ROM. So each control word is 14 bits, and out of that, what all are those 14 bits representing? That's what we are going to see. The first 9 bit will be some micro instruction that is used to select the micro operation for the processor. We already mentioned that a micro instruction should contain bits for initiating a micro operation and also for generating the next address. So out of that 14 bits, some bits should be to initiate a micro operation and some bits should be to generate the next address. So that some bit is this 9 bits. The first 9 bits is used to specify the micro operation, and the next 5 bits is used to specify the or select the next address for the control address register. So we use a register specially for this this circuit, that is control address register. This CAR will be having the address of the next instruction. Okay, that is the for generating the next address, that is the next address that will contain the next control word that will be present in the CAR. So once again, bit 1 to 9, the control word is used to represent the micro instruction or the operation. 10, 11 and 12, 3 bits are used to select the 8 words. 13 and 14 bits are used to select the multiplexer units. Okay, so those are selection bits for multiplexer. We'll see in detail what all are that. Okay, so control memory consists of 8 words. So in this specific case, we are going to design a control memory that has 8 words by 14-bit ROM. So this each word has got 14 bit, and this is the information regarding what all are present in that 14 bits. So now let's see the hardware configuration of that. This is the hardware configuration. This is an 8 by 14 ROM which is used. That is, it has capacity to store 8 words. Each word will have 14 bits. This is the 14 bits that are present. Okay, the first bit is an initialization bit. Then the remaining bits, I hope you remember what S2, S1, S0 all are present. These are nothing but the columns that were present in the sequence of the register transfers, which we saw in the previous video. That is, in the hardwired control or in the one flip-flop per state method, we discussed a table. Those table contains these particular column values. I hope you remember. So these are those column values. And 10, 11, 12, just previously I told 10, 11, 12, 3 bits are used to select the next address, and 13 and 14 bits are used to select the multiplexer values. Okay, so based upon this, how are we going to operate? So let's see how this particular hardware configuration will work. Okay, so the control address register or CAR will hold the address for the control memory. So this CAR is holding the address of that control word. Okay, so this CAR can have two things: either it can have a load input or either it can have an increment value. So when this load input is enabled, it means that an address from this 10, 11, 12 is being loaded into the CAR. Okay, only when this load input bit is enabled, an address from 10, 11, 12 is being enabled, and then it is given to the control address register. If this load bit is not enabled or if it is disabled, then whatever is the address that is present in the CAR, that is just incremented. So these are the only two ways by which you can adjust the values in the control address register. Either you can load it from the input or either you can increment it. Okay, now the bits 13 and 14 select an input for the multiplexer. Okay, so the bit 1 provides the initial state condition denoted by variable X and also enables the external addresses when QS or QA is equal to 1. So let's see what that means. We know that the control address register, when this load input is enabled, the CAR will be loaded with an address from this 10, 11, 12 bits. Okay, now here we see a lot of other gates also. So this is nothing but if an operation is a subtraction operation or if an operation to be performed is an addition operation, based upon that the QS and QA bit will be set. We know that if QS is set, it means that it is a subtraction. If QA is set, it means that it is an addition. Okay, so under the initial condition, when X is enabled or when X is 1, and if QS and QA is 0, 1 and 0, an AND gate, definitely you get a 0 here. Those zeros are being given here and here you get a 0, 0, 0. Similarly, here also if QA is 0, we get 0, 0, 0 here. And once 0, 0, 0 is given, then the address loaded from here is also 0, 0, 0. Then the control address register remains as such. So that is what is meant here. When x is equal to 1 and qs is equal to 0, that means subtraction is not there, and when addition is also not there, that is the state is initial state. Then CAR is loaded with address 0, 0, 0. So whenever qs and qa both are 0 and x is in the initial state, 10, 11, 12 is being loaded with the value 0, 0 and 0. So obviously here the control register is loaded here with 0, 0 and 0, and then the CAR will remain in that initialization state. Okay. Now in the next state, when x is equal to 1, that is initial state, and when qs is enabled, that is if it is a subtraction operation, then qs will be enabled. Okay. Then the address 001 is available at the input of the CAR. Let's see how 1 is available. If qs is 1 and x is 1, then obviously this AND gate will produce a 1 output. Here 1, 0 and 1 it is 0, 0 and 1 it is 0, 1 and 1 it is 1. So 0, 0, 1, that will be given to the control address register. So 0, 0 and 1 is given to the control register. X is also given, which is already 1, and also whatever is the address information that is present in 10, 11, 12 will be loaded. So under the case when qs is equal to 1, 001 will be loaded at the control address register, which means that an address will be loaded, that the address is 001 is loaded in the CAR. Now in the similar case, if QA is 1, okay, if QA is 1 and QS is 0, then it will be 010 that will be loaded, because it is 1 because x is also 1, so 1 is here. 0 and 1 it is 0, 1 and 1 it is 1, 0 and 1 it is 0. So it is 010 that is loaded. So whenever QA is enabled, it is 010 at the CAR, and whenever it is a subtraction or QS, it is 001 at the CAR. Okay, so that is how the control address register is being loaded. Now the values with the mux. We have two selection lines, 13 and 14, to select the values for mux. If 13 and 14 selection lines is 0, then if it is 0, then the 0 line is being enabled. If it is 0, you just perform an increment of CAR. So whatever is the address that is present in the control address register, that is just incremented if the mux value selected is 0. Okay. Now if the selection bit is 0 and 1, if 13 and 14, if it is 0 and 1, then the mux line 1 will be enabled. Then you have to load the input to the CAR. Then a new address or control word need to be loaded to the CAR if the mux value selected is 1. Okay. Now if the mux value selected is 2, that is if it is 10, the selection bit is 10, then this 2 is enabled and the S is being enabled. This S is nothing but it is the output of the XOR operation of the sign bit register AS and the sign bit register BS. I hope you remember it from the previous video. If there are two registers A and B that is used to perform an addition or subtraction or whatever it is, its sign bits are stored in registers AS and BS. So if both these bits, both these sign bits are XORed, okay, so XORed, either both these sign bits could be same or it could be different. So based upon whether S is equal to 1, that is if the XOR operation gives you 1, which means that both the signs are different. If both the signs are different, then you have to load the input to the CAR. Then the address bit is enabled and you have to perform a load. Now if both the sign bits are same, then you get an XOR operation with S is equal to 0. In that case, you have to increment the CAR. So once again, I will repeat, if both the signs are different, then definitely S will be equal to 1 and then you have to load the input to the CAR. If both the signs are not equal, or if both the signs are same, then you have to increment the CAR. Okay. So this is the reason why I asked you to go back to the previous video and just refresh and understand the concept of S and E, because it is from the previous video. I'm not repeating it again. Okay, so S is the sign bit representation and E is the overflow bit, which is used in the next selection line. So in the next selection line, if 13 and 14, if it is 1 1, then the selection is E is being selected if E is equal to 1, that is if an overflow is present. If you perform an addition and if an overflow bit is set, then E will be equal to 1. And if E is equal to 1, then you have to load an input to the CAR. Then you have to load an address into the CAR. If there is no overflow that has been generated, then E will be equal to 0 and you can just increment the content of CAR. So it is basically the content of the CAR that is getting changed every time. Okay, either it will be loaded from the address line or it will be incremented. So based upon the conditions here that has been selected in the mux. Clear? Okay, this is the explanation for the mux which I have already explained. This is how the table for the mux is being present, that is based upon the selection lines 13 and 14. The different selection functions of the mux are being present. Now we are going to the microprogram. Okay, so in the microprogram, in the previous video we studied how the hardware implementation was there, right? We came across a flow chart and based upon the flow chart we draw a transition state diagram, and from the transition state diagram we came across a register transfers, we drew a table, and then we designed the set of flip-flops that were required likewise. So in a microprogram we are not going to do anything like that. We already have that algorithm. So based upon that algorithm we are just going to write a program. Okay, so this is how the symbolic microprogram for control memory looks like. Don't get worried about these micro instructions. These are the same micro instructions from the previous algorithm which we studied. That is addition or subtraction of two signed bit numbers which we have studied. Those same steps are repeated here. Okay, so the ROM address 0 here represents this particular micro instruction. That is the first micro instruction. If in the initialization state x will be equal to 1 and if qs is equal to 1, that is if it is subtraction operation that need to be performed, you should go to the ROM address 1, and if it is an addition that is need to be performed, that is if qa is equal to 1, then you have to go to the ROM address 2. Okay, so accordingly you have to perform the operation. So based upon whether it is an addition or whether it is a subtraction, correspondingly you go. If it is a subtraction, then first thing you have to do is to take a complement of the sign bit of the B register and store it in the BS register. If it is an addition, then directly you can go to the okay, if it is an addition, then you are going to compare the S values, that is the sign bits. If the sign bit XOR value is equal to 1, which means that if both of them are having different values, okay, then both of them are having different values means that it could be either an addition or it could be a positive sign or a negative sign for those registers. So S is equal to 1 means you have to go to 4 to perform a subtraction. If S is equal to 0, which means that XOR operation gave a 0, so the sign bits are same. If the sign bits are same, then you can directly go for an addition, that is A can be added with the content of register A and content of register B. So these are nothing but those steps in the flowchart that has been repeated, and it has been each of these micro instructions are given and represented in terms of a ROM address. That is 0 ROM address is the first instruction, and first ROM address will be the second instruction. Likewise, all those 7 instructions are just given with the ROM address. Okay, now we can't just give these micro instructions directly to the control memory, right? We can't store this to the memory as such, like x is equal to 1, qs is equal to 1. You can't give it. You have to convert it into binary format. So that is what we are going to do it in the next section. Okay, that is binary microprogram for the control memory. Okay, so whatever that is being represented in these micro instructions, we are going to represent in form of binary format. All these ROM addresses, these decimal numbers here have been converted into binary numbers, and respectively all these need to be correspondingly changed in terms of sequence of register transfers. So these are the different set of registers that are used. This set of registers we have seen in the previous video of the hardwired control. So just go back to that video just to revise what all these registers meant for, okay, which I am not going to repeat here. So we know that our ROM consists of one control word, and one control word is 14 bits. So all these 14 bits are represented here. We already saw that 1 to 9 are used to select a particular micro instruction. Bit 10, 11 and 12 is used to select a address, and 13 and 14 are used to select the mux values. Okay, so now we'll see how this values gets worked. Okay, so we'll just have a parallel look into all these three tables and then understand. Okay, initially in our case, when X is enabled, it means that it is in the initial state. Okay, in the initial state, all other registers are cleared, or it is 0. The address that is need to be loaded is 000. We saw that when no addition or when no subtraction is there, the address that is being loaded to the CAR is 000. And the selection line, if it is 01, it means that if it is 01, it means that load the input to the CAR. Okay, so this 000 need to be loaded to the CAR. Okay, that is what is meant by 01. Okay, now next in the next one, this is the first instruction that took place. Okay, now the next instruction is you have the ROM address 001. In 001, at that particular address, what is the instruction that has been stored? The instruction that has been stored is this particular instruction. In that you can see that only the Y bit is being set. Okay, so Y bit is being set in case of this particular instruction. When the sign bit of the B register is complemented, we learned from the previous video that it is the Y bit that need to be set. So that is the reason why only Y is being set and all other remains as such. Okay, and the address that need to be loaded is 010. So 010 is the address that need to be loaded in that case, and the selection line is 01. If the selection line is 01, it means that loading the input to the CAR. So whatever is present in this address line, that need to be loaded. So the current address is 010. Now that 010 will be loaded to the CAR. So 010 will be loaded. So now the ROM address will be 010. Okay, inside the 010, we are performing a comparison operation. We are just checking the value of the sign bit. Okay, if S is equal to 1, that is we are performing the XOR of the sign bits. If S is equal to 1, then you are going to step number 4, that is you are going to perform a subtraction. If S is equal to 0, we are going to perform an addition operation. So in this case, that particular instruction, that comparison, it doesn't require any registers to be set. It is just a comparison operation. So none of these bits are being set here, and the address that need to be loaded is 100, and the selection line is 10. Okay, when the selection line is 10, let's come back here and see. When the selection line is 10, and if S is equal to 1, you can load the input to the CAR. Okay, if S is equal to 0, you need to increment the CAR. Okay, so what is the current value of the CAR? The current value of the CAR is 100. Okay, 100, and the selection line is 10. Okay, so loading the input to the CAR, loading the input to the CAR is done if S is equal to 1. But if S is equal to 0, in our case the S is equal to 0, in that case what you have to do is you have to increment the current value of CAR. What is the current value of CAR? The current value of CAR is 010. You have to increment this 010 to get the next micro instruction to be executed. So when you increment it, you get the ROM address 011. So in 011, whatever is the micro instruction that is stored, that need to be executed. Why we incremented it? Because in this particular case we got the case that if S is equal to 0, if S is equal to 0, then you have to increment the CAR. So whatever that was present in the CAR was having 010, so that need to be incremented. And when that need to be incremented, in that particular case, the next condition that need to be checked is whether this one A is incremented with A plus B, or A is loaded with A plus B, and then if a carry is present, that carry is loaded to the E register. So that particular operation is represented here. Okay, that particular operation is represented here, and then the address that need to be loaded is 000. Okay, so the address that need to be loaded is 00, and the mux selection value is 01. So whenever 01 is present in the mux, what is that? Load the input to the CAR. Okay, so loading the input to the CAR need to be done. Okay, loading the input to the CAR if in case of 01. Okay, so in that case we are going to now next increment the ROM address. Now it is 100. In 100, what you have to do is, in 100, the next instruction that need to be checked is this particular instruction. So what you have to do is, you have to perform a 2's complement, and also you have to do a clear bit also. Okay, so that is being performed here. So that particular operation is represented in binary format here, and the address that need to be loaded is 101, and the mux line is 01. Okay, so whenever the mux line is 01, what you have to do, you have to load the input to the CAR. So what was the present in that address line? 101. That 101 address need to be loaded to the CAR. So 101 becomes the content of that CAR, and inside that 101, it is just we are performing a comparison operation of E is equal to 1. If E is equal to 1, then you can go back to the initial state. If E is equal to 0, you have to do the remaining steps. So that particular instruction is being represented here. So whenever E is equal to 1, you have nothing to do, and finally you are doing a reset of E. That reset of E is being enabled using the W register. Okay, so all these values are actually the repeated values from the sequence of register transfers that were present in the previous video. So those values I have written it down. This is nothing new here. Okay, so only thing is that it is based upon these address and these selection lines, the addresses are getting loaded. That is the only new thing that is happening here. So based upon the selection lines, addresses will be loaded. That's all. Okay, and all these operations are performed in sequence. So all these respective addresses need to be loaded here. So now after that, this fifth step, what you have to do is, if suppose E is not equal to 1, then you have to perform these two steps that is being represented here. So if it is 1 1, what do you do? If 1 1, in that case, loading the input to the CAR if E is equal to 1. So if E is equal to 1, you can load the input to the CAR, otherwise you have to increment the CAR. So here E is equal to 1 case is over. Now we are going to consider the case when E is equal to 0. If E is equal to 0, what you have to do? You have to increment the content of CAR. So that is why you have incremented the content of CAR. 101 plus 1, when you increment it, it becomes 110. So now the content of the CAR is 110, and in 110, what are you performing? You are performing all these steps. So those steps need to be represented as such in the binary format, and the address that need to be loaded is 111, and then again the selection line is 01, and the selection line you have to load the input to the CAR. So whatever is present in this address, that need to be loaded here. So whenever it is a load input to the CAR condition that is present, then you have to load the respective address to to the ROM address. Whenever there is an increment that is present, the current address is incremented with the 1. That is the only function that is happening in this particular section. Based upon these selection lines, either you increment the CAR or either you load the input. How do you get those load address? It is present in this particular bits. 10, 11 and 12 give you the address bits that need to be loaded to take the next micro instruction. Okay, so that is based upon how you will form this particular table. So this is my binary microprogram for control memory, and this is the symbolic microprogram for control memory. Okay, so this is all what is need to be written in case of how you can design a control logic based upon the second method, that is microprogram control organization. So first you have to write down this particular hardware configuration and how this control address register values are being loaded, that you have to specify. Then after that you have to give this symbolic microprogram for control memory. This is just the same microprogram which we studied in the previous section. So based upon that, ROM addresses are also given, and then you have to draw this table to show how these each micro instruction are being represented in terms of binary format. This table also needn't be by hearted. This is based upon the logic which we discussed in the previous video. Okay, this is not something which we have to by heart as such. Please refer the previous video and understand how this binary values were being given with respect to each of these operations. Okay, then you'll have a better idea.